Okay. So we're talking about domain-independent planning. We're talking about, and the whole point of domain-independent planning is you take this domain, and then the question is how do you derive a heuristic? And we talked about a whole bunch of heuristics. We talked about 0, which is like the world's most boring, lame heuristic. We talked about number of unachieved goals, which is inadmissible. We talked about H1 max. Is H1 max admissible?
Yes.
Yes. What about H1 sum? We talked about a plan. Last time we talked about planning graphs at great gory length.
That's admissible.
Max is, yeah. So if you take for every goal literal the layer it appears in the graph, and then you max over all the goal literals, that's admissible. If you sum, it is not. Forming a relaxed plan, we talked about at the very end of class. And so let me just mention that again, just in case people were not listening. We're going to actually extract actions that support the goal literals out of the planning graph. So first of all, we're going to build a real planning graph, not just this little dinky reachability graph that you do for H1. We're going to do a real honest-to-goodness planning graph with mutexes. And we're going to keep going until either the graph levels out or all goal literals are non-mutex with each other. And then we're going to pick out actions that support the goal literals and collect them together and count how many they are. And that's the heuristic value. And you extract those actions by using no-op when you can. So here, for example, we wanted to have our cake and eat it too. Having can be achieved by a no-op. So we'll choose to put no-op in our plan. Now, the only reason that doesn't work is because no-op is actually mutex with, well, no, we can use eat. We can use, no-op is actually mutex with both ways of getting eat. So actually, we're not going to be able to include no-op. We're going to have to include bake, because bake is not mutex with this way of achieving eat. So we'll pull out bake and this no-op, and that means we need these two things, which are both achieved by eat. So the relaxed plan will be eat, bake, which is actually the true plan in this instance, which is pretty cool. So anyway, extracting the relaxed plan is actually slightly non-trivial because you need to be checking mutexes. Finding the optimal relaxed plan is NP hard, so nobody does it, but people use this greedy algorithm with just choosing no-op if you can, reusing previously chosen actions if you can. Anyway, it's a fabulous heuristic. It's not admissible because no one actually goes to the trouble of forming the optimal relaxed plan. Although actually there was just a paper this last year at the planning conference where somebody found an algorithm that could derive the relaxed plan for a very large class of planning problems, could derive the optimal relaxed plan in polynomial time for a certain class of problems. You can imagine people trying to prove stuff. If you're into theory, like you look at the operators, and if there's a certain relationship between like the number of preconditions and how many actions there are to support things, and whether every action has an inverse action, you can imagine looking at the operators and trying to derive some properties that would let you say whether finding a relaxed plan is going to be hard or not. You can imagine such a result. Anyway, so that's the relaxed plan. We talked about it yesterday. Taking the max over the goal literals, taking the sum over the goal literals for the planning. So this is the reachability graph. This is the real relaxed plan heuristic. So we have a bunch of different ways of finding heuristics now. So that's forward state space domain-independent planning. That's assignment 3. That's everything.